So welcome to the course today on the first part of our lecture looking into the iterative closest point algorithm. So the iterative closest point algorithm is a technique for aligning sensor data such as laser range scans, and therefore they play an important role within the simultaneous localization and mapping or 3D reconstruction problem. Okay, so let's have a look. Why is this important? What is relevant in here? So the goal of these alignment algorithms is to take points, for example, from the 3D world, but could in theory also be a 2D scan, and try to align them so that the points, the data points that are observed, the 3D points in the environment, for example, are aligned with each other. So that means they lie on the same position. So one example is I take a scan here from the position where I'm standing, consider I'm a robot and observing the environment, and I take a second scan, let's say from here, observing the same part or a similar part of the environment. Then I will have two scans, which I've taken from similar positions, observing the same part of the environment. And the goal is to actually find the transformation so that the endpoints that are perceiving the same object in the environment are aligned with each other, so lie on top of each other in the same position. If I do this, I can basically recover the relative transformation between the two recording positions. And this is information that we will later on use as so-called virtual observations in the graph-based simultaneous localization and mapping problem. So the ICP approach is a technique for solving the alignment problem of data points, 3D data points. So the goal is to find the transformation between the two point clouds or the two scans so that the corresponding points align. What is a corresponding point? A corresponding point is a point that I have in two, or are points that I have in two scans, and they are expected to correspond if they refer to the same point in the 3D world. And there are different techniques how we can actually solve this problem. So you can treat this as a least squares problem. You can do robust least squares estimation. But a very common technique is a so-called ICP or iterative closest point algorithm. And we will get an idea today how this approach works and how you can actually implement this approach. So why is this relevant for us? This is very important in the context of mapping or SLAM. So typically you don't have a single sensor reading, such as a single 3D LIDAR scan to observe the environment. You will record multiple scans from multiple different locations because you want to scan the object or the whole scene, and typically one scan is not enough. So if you do not know the exact position from where those scans have been taken, you need to actually solve the problem on how do you need to shift and rotate the individual scans so that they build a consistent global point cloud. So you can see a few examples here where the ICP algorithm have been used. So on the top, these are building structures taken from a robot equipped with a laser range scanner driving around, mapping the scene. Or here you have shown the individual locations of a mobile robot navigating through the environment, taking local 3D scans, and basically stitching those scans to each other. And the stitching process, this alignment process, is what the ICP algorithm does. As an illustration, you can see here on this side two surfaces, one colored in gray and the other one colored in yellow. And you can see how the ICP algorithm actually aligns those scans by slightly shifting and rotating those two scans with respect to each other so that those scans then are going to overlap. So you can see this in this small animation, and you can see through a sequence of shifts, one scan or one point cloud has been transferred into the coordinate system of the other point cloud so that the points which correspond to the same point in the environment are actually at the same position. So you can see this here in this yellow grayish texture which is overlaid. And the question is, how do we do this? How do we generate this process over here? And that's what the iterative closest point or ICP algorithm is about. It's an algorithm which has been around since quite a while, so it's not something extremely novel, and it's there to align local point clouds or surfaces with each other. Again, this is the example. The goal is to define this iterative process, and this is what gives the name the I, in order to start from this initial location and end up with those aligned skins here. Okay, so let's dive into the problem and see how that can be solved. So we assume if we're having two sets of point clouds, a point at Q and a point at P, and Q is, for example, taken from the first scan and P is taken from the second scan. And we assume at the moment to also have so-called correspondence information. That means we know that, for example, a point I in the first point cloud corresponds to a point J in the second point cloud, or index I and index J. That means we have a set of pairs of partners of IDs, which tells us a certain point in scan number 1 corresponds to a certain other point in scan number 2. And this is this correspondence information, or something we also refer to as a data association, which is a very important part, a very crucial part to have that information. And what we then want to do is we want to find a transformation that transforms one point cloud into another point cloud. So here in this equation, you can see we have an error function that we want to minimize. And this error function depends on a rotation matrix R and a translation vector T. So we are talking here, for example, about a 3D rotation, 3 rotational angle, and a 3D shift translation, so 3 translational components. So this would be a 6 degree of freedom transformation for the 3D alignment problem. If we're in 2D, it would also only be 3 degrees of freedom, x, y, and 1 rotational component. But let's stick now with the 3D formulation. So the error is then given by the sum over all corresponding points. So because we're only considering points for which have a corresponding partner in the other scan. And then we try to take the points P and Q and find a transformation that we can rotate and shift the individual scan. So we're rotating use the rotation matrix to rotate the point P and shift it by T, so that then they are aligned in the same coordinate frame. And we want to minimize the squared error. So that means the difference between the point in scan number 1 and the transform point in scan number 2 into the coordinate frame of 1, and then these distances between those points, between all corresponding points, all those small pairs. We want to minimize the sum of their squared error. Okay? So, key idea, assume we know those correspondences, and if we assume they are correct, let's say we have 2 surfaces, the blue surface and the red surface over here, and those black lines here indicate those correspondences. That means this point in the red scan corresponds to this point in the blue scan, and in the same way down here. So we want to find the transformation which minimizes the sum of the squared distances of these black lines over here. So that by, for example, taking the red scan and shifting it and rotating it upwards so that it overlaps with the blue scan, we would get a solution which looks like this. And this is now, in this illustration, the minimum error configuration, because all those black lines actually are 0. And in reality, of course, we don't get them down to 0. We always have noise in our sensor data, but we want to actually minimize the squared errors. Okay, so all the questions, how do we actually do that? How do we obtain the translation and rotation parameters to turn this situation into this situation? And that's what the iterative closest point algorithm is about, or let's say what one key ingredient of the iterative closest point is about, because this so far is not iterative. This is just an alignment step giving those correspondences. And so how does that work? We can do 2 things. We can take the center, compute the center of mass of both scans, and actually subtract the center of mass from every scan. So what happens? So we compute the center of mass of scan number 1, we compute the center of mass of scan number 2, and then we subtract the center of mass from the individual point set. That means both point sets will be shifted on top of each other so that they have the same center of mass. And this is kind of the key step that we do in order to obtain the alignment of the points in terms of the translation. And then the second part is we need to compute a rotational alignment, so we need to rotate those 2 scans on top of each other so that the error in those points actually gets minimized. So first, let's have a look to the center of mass. It can be done quite easily. We compute the center of mass by taking here into account only those points for which correspondences exist. So all the other points are ignored. We are just doing this for the points for which correspondences are available. So we sum up over all points in Q and then divide by the number of corresponding points. This gives us the mean of the points in Q, so the center of mass of Q, and we do exactly the same thing for P. So iterating, summing up all points for which a corresponding partner in the others can exist, and then we obtain dividing it by the number of correspondences or points we are considering, so that we end up with the center of mass of the point P. And then we can generate 2 new point sets, which are the primed ones, Q prime and P prime, which is basically the original point set minus the mean. So we are basically subtracting the mean from every data point. So as a result of this, the new point clouds, the primed ones, Q prime and P prime, are point clouds where the center of mass is 0. and both have the same center of mass. So it corresponds to shifting those points on top of each other. So given this center of mass reduced point sets Q prime and P prime, I can actually look into something which is called the orthogonal Procrustes problem. And it's a variant of the original problem, and I can show that if I solve the orthogonal Procrustes problem, I actually solve my original error function using this center of mass reduced point sets. So the original error function was this one shown over here. So I'm summing over all correspondences and rotate the points P into the coordinate system of the point Q, and I want to find the R and T that minimizes this function. If I now operate on the center of mass reduced point set, I can use an equivalent formulation, which is the following shown over here. So error function E prime, now only taking the rotation into account. So what this expression here means, these are all the points from Q prime stacked next to each other. So it's a matrix of those points. And I subtract from this the same matrix generated from the points at P prime with a left multiplication of this rotation matrix. So what does this expression do? This rotation matrix rotates all the points in P, still keeps them in this matrix form, and then I subtract those two matrices with each other. And then I'm computing the Frobenius norm, which is a norm obtained by computing the difference between the elements of two matrices. Well, in this case, two matrices, but since I subtracted them, it's basically summing up the elements of the resulting matrix. And so, given that I used the squared norm over here, we are obtaining the squared differences between the one point set rotated on the other point set. So you can see that's actually equivalent to the original problem when I already subtracted the point sets. And so minimizing this expression, computing R for this term, gives me the same R than the one over here. And this one I can solve with something which is called the orthogonal Procrustes problem. And there exists an efficient solution using the singular value decomposition. So how does it work? So first I need to compute the so-called cross-covariance matrix from the two mass-reduced point set. So I'm summing over all corresponding points in Q and P and call Q prime times P prime transposed. So note that compared to the dot product, the transposition operator sits here on the outside, not on the inside. And so this gives me the cross-covariance matrix of the point sets. And then I use SVD to decompose this point set. So I execute the SVD on this matrix W, and it gives me three matrices, U, D, and V transposed. And the product of U, D, and V transposed gives me my original matrix W. And so the individual matrices have different properties. So first, this matrix D, the one in the middle, is a diagonal matrix which contains all the singular values, but that's something I'm not really interested in at the moment. I'm interested in this matrix U and V, and these are 3 by 3 rotation matrices in this example over here, under these conditions. And if I multiply them with each other, so U times V transposed, I actually obtain my rotation matrix which minimizes this function. This holds only under the assumption, of course, that my cross-covariance matrix has 4 rank. So if we talk about 3D points, it must be rank 3. If we're talking about 2D points, it must be of rank 2. And under this assumption, this matrix R can uniquely be determined. And once I have this R, I can also compute the translation vector by transferring the center of mass in exactly the same way. So this allows me then, based on the orthogonal Procrustes problem, just by using singular value decomposition, to obtain R and T, and in this way align our point sets. So to sum up, what do we actually need to do if we want to implement this? First, we need to compute our cross-covariance matrix of the center of mass reduced point sets. Second thing, we compute the singular value decomposition, but we are only interested in the matrix U and V transposed. And we multiply U and V transposed, which gives my rotation matrix R. And once I have R, I can update my point set P in a way that I reduce the mean of P, perform the rotation, and then add the mean center of mass of Q, which gives me my new point set Pj or P, which then is in the coordinate system of Q. So I shift P onto Q. So also as an illustration, what happens, we have here 2 point sets, the red one and the blue one. And so we're transferring the red one onto the blue one. The first one is a translation that we shift them on top of each other. There's a translational part. and then we have the rotational part that they rotate on top of each other. So you see here the blue and the red points are very well aligned. You will see some small black lines remaining. This is the remaining elements due to noise in my observation process, because my observations are not perfect or the points are not equally sampled from the original surface. So some small errors will remain, but this is the optimal solution that I actually get out. So the optimal translation and rotation that minimizes my error function. And again, this works assuming known data association. So we assume to know our correspondence set. And if we know our correspondence set, this is the way how we can compute our solution. The problem in reality is that we don't know this data association. So if we have data association, everything is easy. If we don't have the data association, it becomes more tricky. And this is something a problem that you have in all real-world situations, that you have to deal with this unknown data association. And the problem that we have in here is that the correct data association, if it is not known, we typically can't do one step in order to come up with the right solution as we did it before. What we, however, can do, we can try to guess the data association and then performing a correction giving this guessed data association in the hope that the new alignment is better than the old one, given that our guess of the data association was not too bad. And then use an iterative process to come up with a solution. So how does it work? So consider you have this blue surface and the red surface. And you take your points on the blue surface and look for the closest point on the red surface. So for this point, the closest point on the red surface is this one. For this point, the closest point on the red surface is this one, and so on and so forth. This is obviously not the right data association, but the hope is that we start with this data association as an initial guess and perform our corrections. We are kind of getting better and better step by step. And so if I have this data association and I compute the SVD solution as before, assuming it is the right data association, I will come up with an alignment which looks like this, which you can see is already better than what we had initially. And so the idea that this is a better setup than this one, so we can restart the process looking for data association in this setup, in this alignment, and then get better. So if we now start with this initial alignment and look for new data associations, we will get a solution which looks like this. So you can see here this data association is not perfect, but it's clearly better than what we had initially. So it's better than this one, this data association over here. And so we take this data association and again perform exactly the same step of computing the alignment of the 2 point clouds. And we iterate this process over and over again so that in the end we come up with a hopefully perfect alignment of the point clouds. And this is kind of the key idea of the ICP algorithm. So we know how to align 2 point clouds given the data association. Given that we don't know the correct data association, we guess it based on an initial guess. And then perform an alignment, assuming the data association would be correct, which gives me 2 new point sets. And then I simply repeat the process, assuming this alignment should be better than what I had initially. So I recompute my data association, then compute my translation parameters, and iterate this process over and over again. So that after a while, those 2 point sets are aligned as close as possible. And this is the idea of the iterative closest point. That's also what gave it its name. It's iteratively making a closest point data association and then use the SVD approach in order to compute the alignment. And the hope is if the initial configuration, so the initial guess of the data association is good enough, so if the point sets are close enough, we will actually converge to the right solution. But there's no guarantee for that. There's no guarantee that this is actually the right solution, and we just can have the hope that we are close enough to get the right solution. So it's not guaranteed that we get the optimal result, but it's kind of an approach where we guess a data association and perform it iteratively in hope we get better and better over time. So if you put this into an algorithm, it would maybe look like something like this. We start with an initialization of our error value. We say, while the error decreases or has decreased in the last iteration and the error is still larger than a certain threshold, then we are actually continuing our iterative process. So what we do, we determine our corresponding points. This can be, for example, taking the closest point in the other point set given the initial guess. This is a standard approach that we can do. Then we compute the rotation and the translation vector using this SVD-based approach that I just explained before. And then we apply this rotation and translation to register or line those point clouds. And then we can compute an error value, which is basically this error function that we're trying to minimize. So what is the sum of the squared errors between the corresponding points? And so I will start with a high error value, it's infinity in the beginning, and then after the first alignment, this error will be smaller. And then I enter the while loop again, say yes, the error has decreased, because from infinity to something smaller, and assuming the error is still larger than a certain threshold, I again look for new data associations, given my better solution that I have, compute rotation and translation matrix, apply them, compute the error again. And I continue this process until the error doesn't decrease anymore, or the error is smaller than a certain threshold. And we can also check if the data association doesn't change anymore. So if this data association stays the same in 2 consecutive steps, the error will not decrease because we will get the same solution. So as soon as the data association doesn't change anymore, we are actually done with our problem. So just a small example how this looks like. So what you see here are 2 scans shown in different colors. This is actually a top-down view. These are kind of 2 buildings here. This is some bushes on a sidewalk. And you can see how the approach iteratively aligns those 2 scans taken, in this case, from a 2D laser range scanner. So it's a top-down view. The kind of bluish things and the yellowish things are the 2 different scans. And this is kind of how the iterative closest point approach works. You should, however, note that there is a large set of variants of ICP, because the variance mainly comes from the fact is how does this correspondence look like, and how do I compute my error function. So the error function now was a point-to-point error function, what we have shown. So we're basically computing the distances between 2 corresponding points. There are alternatives to this that I can, for example, say, assuming that we have surfaces, what's the distance between a point towards a plane, assuming that the surface is a plane and have 1 point, a distance to a plane. Especially for sparsely sampled point clouds, this becomes relevant because we don't want to introduce an artificial error just because there was a low sampling density on one of those surfaces. So in those examples, it may be better to compute the distance from a point towards a plane. And again, there are a large number of different variations what I can change. So one of the things is, for example, I may not want to use all points. You may think, okay, why is this a good idea to reduce the number of points? The more measurement, the better. It's kind of the initial intuition. But this can have several reasons why I may want to reduce the number of points that I'm considering. This can be due to speed, but it can also be due to different densities of points. So if I think about a typical laser range scanner, scanning points in the environment, points which are nearby will give a higher density than points which are further away. And I may want to give the surfaces in my near surroundings not a higher weight just because they are more points like on the surface because of the properties of this. So this may be a reason, for example, to consider only a subset of points and, for example, doing a uniform subset. The other thing I can take into account is weighting the correspondences of those points. So depending on the uncertainty that I have about my points, either measured points or maybe I even have some uncertainty information about the data, I may want to exploit this and, for example, weighting correspondences higher when I'm very certain about the data association or the quality of the 3D points, and maybe give a lower weight to points where I'm less certain about it. Again, different ways on how to do the data association, like this point-to-point or point-to-plane, are two examples for this. And I may want to also take outlier rejection techniques into account. So in practice, we will make data association mistakes. Even if we have a very sophisticated data association technique, there will be errors in our data association. This can be due to the case that the environment actually changes. So consider you're taking a laser range scan and persons are walking by and walking through your scans. So if you take the 2 scans at 2 different points in time, the person has moved and therefore corresponds to the same physical object, but the physical object has moved. And then you will introduce errors in your scan if you take them all into account, assuming that the points would be steady. But there can also be other reasons. Occlusions can also be an issue. So we are likely to make data association mistakes, and the question is, how do we reject those outliers or gross errors that we may find in our scans? And so there are different variants of the ICP algorithm, and I want to discuss a few of them now in a little bit more detail, at least give you an idea on what's going on here. So again, there can be different reasons why I want to perform. Take into account those variants, as I said before, speed. If I reduce the number of points I'm considering, my approach is obviously faster. This becomes important for real-world application where speed matters. For example, if I have a 3D LIDAR scanner which takes a large number of points, 10 times, 20 times per second, I may need to reduce the number of points I'm considering in this alignment procedure. Stability, local minima may be an issue, or that I give too much weight to certain local structures because just they have a higher sampling density based on the principle of my laser scanner. This can be an issue. Maybe some information I have with respect to noise or outliers. If I, for example, can estimate that some objects look like a person or pedestrian, I may want to take them out of the registration procedure if I'm moving through an urban environment, because these are objects which are expected to move or are most likely moving. And so I can take this additional information into account also for treating certain objects as potential outliers. Or we may take steps for increasing the basin of conversion. So what's the maximum initial misalignment between the scans? So how bad can our initial guess actually be so that the approach still converges to the right solution? So let's have a look. Let's start with subsampling points. So different techniques I can use. I can, of course, use all points. This is kind of the standard approach of all points, for which I have correspondences, should be the correct term in here. I can perform a uniform subsampling so that I have, for example, a uniform distribution of points over the space. This would be kind of one of the approaches if I don't want to give a higher weight to certain structures just because they have been closer to the sensor. I can do a random subsampling, which is basically easier to implement, so you may want to go for that. We can do sampling based on certain types of features. Let's say I have certain objects which are more important than others for my alignment, and of course I can take that information into account. Or what's often done is a normal space sampling, that I basically have a higher density of points where the normal structures, so where I have surfaces with a high curvature or with strong curvature, because they're typically better suited for the alignment. I'm actually sampling more points in those regions compared to, let's say, very flat, large surfaces. That's also something that I can do. So there's one example over here. If I have two scans and they look like this, and a uniform subsampling may generate data associations which look like this. In normal space subsampling, you can see that the density of the data association points are higher in areas where change or a stronger change in normals. In areas where there's no change in the normals, the amount of data associations is smaller, and this can be used to get in better alignment, especially if I have large smooth surfaces. So there are two examples over here of very flat surface where you can only see those small carvings in here. And again, red is scan number 1 and green is scan number 2. What you can see in here is the alignment doesn't look too bad, but you can see here in those areas that actually the carvings are not perfectly aligned. And if I take this normal space sampling into account, so that I'm actually considering more points along those carved lines, I actually get a better alignment of the two scans. So this is kind of one example that I can do. I can actually zoom into those two views, so I kind of have this zoomed in view. You can see here the misalignment of the carve compared to the proper alignment if I take the normal space sampling. And that's kind of one example how I can improve my data association by using this additional normal information, because areas of strong curvature typically allow me to align my scans better. The other idea is to use some feature information for sampling points on features. So this is one example of here a 3D scan. Again, this is actually the example that we have shown before. Here you may remember this view initially. So this was a 3D scan taken in a local environment, actually on the Freiburg campus of the computer science department. And the idea here, that's the work which goes to, has been done by Patrick Pfaff, where he was taking into account features or extracting certain features and then trying to align only those points where the features are actually similar. So this can be, for example, poles or certain structures. This can be flat walls. So they basically only look for correspondences of walls against walls, or poles against poles, or whatever, ground surface against ground surface. So you can actually do this to increase the likelihood of making the right data association and using this as an initial step to then align your scans in a better way. This has certain advantages. Typically, it is faster because the number of points for which those features exist is much, much smaller. Also, you decrease the probability of making a data association because you're not looking for one point in the whole other points that for correspondences, but only in the subset where you have a similar feature value. But of course, it requires or makes the assumption that you can determine your feature values or semantic classes or whatever you're using at a high accuracy. If this is not the case, you would obviously fail or even make the results worth. But this, in this example, allowed to dramatically reduce the processing time by just considering a much smaller number of points, at least for all the initial steps of the ICP algorithm. There's another example how scans can be aligned. It's an example by Andreas Nüchter, scanning through a cave or underground environment, and then you always see kind of the new scan in blue comes in, and this point cloud is registered against the point cloud built so far, and this way you can incrementally map the environment. And this approach uses a uniform sampling, again, to avoid that we give it too high weight for areas which are nearby the scanner rather than those which are further away. Okay, the second thing I want to look into the ICP variants is kind of weighting of correspondences. So what we may want to do is we want to give a higher weight to correspondences which we where we know have more information about the points. For example, for points where we can estimate their 3D location more accurately. This can, for example, be the case when you have a stereo camera. In a stereo camera, you, for example, have the setup that the points which are further away from the camera have a higher uncertainty in respect to their position, especially with respect to their depth information, and also that component. And so you may want to give them a smaller weight if they're further away, because you simply can't determine their X, Y, Z position as accurately as you can do it for points which are closer. So you want to give them a lower weight. So again, this weight can be taken into account based on my sensing principle, that I know that certain points are scanned with a higher accuracy or a smaller accuracy. Same holds, for example, for depth cameras such as the Kinect camera or a similar setup, where you can see the uncertainty of the points increasing with distance or the noise that you have. So you want to take that into account. This effect is less prominent for laser range scanners typically, or you may have some other information that you can take into account about your points, so that you can assume them to be outliers and then actually downweight those points. So also some robust estimation techniques can, for example, be used, which then can be turned into a weighted minimization problem, which is actually pretty related to this reweighting, what we can do. But typically it requires you to have some additional information about your sensor or uncertainties of those points. For example, if you have, a covariance matrix for every point in 3D, that's one way to take that into account. Data association is another key thing I want to look into, because this is where a lot of approaches actually differ. So how do we do the data association? How do we estimate, given an initial alignment of the scan, so an initial transformation between the recording poses or between the point clouds, how do we actually get this initial data association, this correspondence set C, which I haven't really talked about a lot. So the absolute standard approach is what is called the closest point. This is also which gave the ICP the name Iterative. So by taking for every point in the first scan, I'm simply taking the point which is closest in, for example, the Euclidean space in the other point cloud, and make this data association based on the closest point. But there's a large number of other techniques that I may want to take into account, like point-to-plane matching is very popular recently, or especially through the Kinect-like style sensors, but also for laser range scanners. We find projection-based approaches where models are projected into the observation space and then try to align them. So there's a large set of different techniques that one may use for doing this. So let's start with trying to find the closest points. We can do this. It basically means that for every point in scan number 1, we need to find the closest point in scan number 2. And this is something you can do, for example, in by using KD trees if you have large point clouds, in order to make nearest neighbor queries efficient, rather than checking in a brute force fashion for the data association. So, for example, we have this point over here, and then the closest point on the red scan sits over here, because any other point on the red surface would be further away from this point. So this is the closest point for that point given. So this is one data association, and we can, of course, repeat this process and make a data association based on this. This is generally okay approach. It's actually not too bad. It's not the best thing you can do, but it requires typically a large number of iterations to be executed in order to perform well, and it also requires kind of a good initial guess. So, for example, if you take those scans and rotate them by 180 degrees, you can, or quite often, generate situations where the approach is not actually working that well. The next thing you can do is something like what's called normal shooting. So you take a point here and then you compute the normal based on kind of the neighboring points and then shoot into the direction of the normal. This kind of depends on which way the sensors have been recorded, so that this normal shooting approach can actually be an attractive way. So you basically shoot the normal up to this point here and then say, okay, this point here would now be my corresponding point, and then this is your data association. So it's typically provides a slightly better convergence result than for the closest point algorithm if I have a smooth structure, so smooth surfaces and a good initial alignment of the surfaces, but typically is not that good, especially for noisy data points. You can imagine this: if you have a high noise here in your data points, you may not be able to actually compute your the direction of the normal in an appropriate way, and this can then lead to problems that you have. You can also do other things. You can compute some, let's say, compatibility measure between points. So if you have additional information like color information, or from a laser scanner, let's say the reflectivity value, or if you have an RGBD camera, you also have the RGB value, the color value for every individual point. Of course, it may make sense to only match, let's say, red points against red points and green points against green points, because this reduces the probability of actually making a data association. So if you have additional information like color information, or maybe you can even extract that from the local surface properties like normals, you can actually use this information in order to avoid making data associations. You can't fully avoid it, but you can actually reduce the risk of making data association. A very popular approach is also the point-to-plane error metric, where you basically minimize the distance not from point to point, but from point to a plane. So why is this relevant? If you think about two surfaces, which are kind of shown over here, especially if these surfaces are not very densely sampled with data points. So if you have a laser scanner which has, let's say, a low resolution, for example, you may find correspondences between the points, but you actually ignore the fact that these are actually surfaces. So if you consider one point set as a surface, let's say this surface over here, then the distance between this point wouldn't be going to this point, but actually would go to that surface. And here as well, that would be the distance you actually minimize. And here it may even fit, roughly at least. So by taking into account that this is actually a surface, you can actually find better data associations, and you don't do basically a residual mistake just because the sampling density of your scanner is low. Because even if you reduce those points with respect to each other, even if these points in the end will lie on that surface, you still have residual errors which kind of pull into directions along the surface a little bit, and it's a rather random process just because your point set hasn't been scanned very densely. Therefore, these point-to-plane approaches are very popular and have actually been used quite effectively. So there are different views of them. So some of them say they're actually slower, or they're actually slower to compute, but provide better convergence rates than the point-to-point approach. And today we can see that the point-to-plane metric is actually probably one of the most frequently used metrics that we can shoot. A last important aspect to consider is the rejection step. So how do we reject outliers? Because, as I said before, in real-world data, we are very likely to. What one can do, for example, is, well, the simplest approach would be, if I have a point-to-point metric, for example, to simply ignore points which are larger than a certain distance. let's say we have here some data associations and here other data associations, by saying that those are actually really large values, those are small values, they're more likely to correct than those. And I'm simply ignoring the red ones. But this can work, this can help you, but it's actually hard to actually find that threshold because it depends how misaligned your scans initially are. And putting in a hard threshold is always something which is tricky to do, or is a good heuristic in some situations, but it actually depends how your data has been collected. And it can have advantages, but also can have disadvantages. So again, rejecting a point that is further than a certain threshold is actually something which is frequently done, but not necessarily the best approach that you can actually do. The other thing one may take into account is looking into compatibility. So do I have certain data associations where points which are nearby on the same surface are actually far away in the other scan? So it's kind of a local compatibility measure. This is typically, again, more computationally intensive to compute, but it can actually help you to identify wrong data associations. There are other techniques such as so-called trimmed ICP, where we basically compute all our correspondences, we sort the correspondences, and then throw away a certain percentage. Let's say the 20% of the worst data associations, so those with the highest initial error, we just ignore them. That's kind of a standard approach that one can use. Then this T is somehow related to your outlier ratio, so this T% I have over here, the percentage I'm throwing away. But again, it requires you to know something about your overlap and your initial data association not to be too bad. So again, this is always a very heuristic approach. It's not always easy to do that in the right way. We will later on in the course learn a technique where we can actually use something, let's say, at least slightly smarter or different techniques to deal with those outliers. So there are different approaches. One approach is a ransack-based approach. It's a sampling-based approach, computationally pretty expensive, but can deal with high outlier ratios. Other techniques are approaches that kind of change the error function we're actually minimizing. We don't go for a squared error function, but take another so-called kernel function into account through which we squeeze our error function so that high errors do not have such a strong impact on the result. And so there are different so-called robust optimization techniques that I may take into account in order to do that. So kind of as the ICP algorithm in sum, how we do this. So initially we potentially don't subsample our points to a smaller point set. Then we are going to determine our corresponding points based on this subsampled point set. We may weight some of those points with additional information. We may want to reject a few pairs, correspondences which are very large. Then we go back to the original approach, compute the rotation and translation matrix and vector using the SVD, the singular value decomposition, and apply this transformation to rotate one point cloud onto the other point cloud. We can then compute our error function and then make a decision, is this error, has this been decreasing or is it still larger than a certain threshold? Then actually repeat this process. Typically, I restart here by determining the correspondences. I typically don't do the subsampling again because it would change my correspondence set completely, and this would lead to a rather unstable behavior. So I'm basically repeating here from determining the new correspondences until I obtain my final result. So if I use this in practice, why is this kind of important? I can actually use this to incrementally align scans, for example, taken from a moving vehicle. Let's say I have a robot which drives around, so we have some odometry information, basically counting the movement of the wheels, and then it takes a 3D scan, then it moves a bit further, takes another 3D scan. So this 3D scan turns into a 3D point cloud at a point in time I, and the system is moving, and typically this movement is very noisy, but gives me an initial guess, and then I can perform an ICP between those two point clouds I and I+1 and align those point clouds. And by aligning those point clouds, using the odometry as an initial guess, I get an improved transformation which tells me how did the robot actually move from here to here. And then I can actually stack that together and build a map of the environment. And this works well for laser range scans that I'm matching on point clouds, or range cameras, RGBD cameras, but also I can take a stereo camera or other data that provides me 3D information, which I can use here. Just a few examples here. What you see here in that system is a robot that we have built to explore Roman catacombs within a European project. And it also used a mapping system taking into account the data from a Kinect-style sensor, actually from 3 different Kinect-style sensors he installed on the front of the platform, perceiving the environment and registering them with help of the ICP algorithm into a consistent set of point cloud, and then running a SLAM algorithm. So here on the side you can see, for example, part of a scan which has been taken from multiple of those Kinect scans. The approach here which was used was so-called NICP, a variant of the ICP algorithm developed by Giorgio Grisetti and his team from Rome, that specially takes into account normal information to improve the registration, make the registration more efficient, just as one of those examples. I also provide you with a small example of how they could work in an autonomous car. So what you see here is a data set, called a so-called kitty data set, where there's a vehicle driving around which has a 3D LIDAR, in this case a Velodyne 64 beam laser installed on the vehicle. And what this approach does, it basically registers the 3D point clouds that are coming one against each other and builds a graph-like structure which is then used in a SLAM algorithm to actually estimate where the vehicle is going. And so far we are still driving open loop. There has been no loop closure or similar information. So all the post corrections here are basically done using the ICP algorithm. You can see, the car drives actually over a bridge over that road. It will drive around. This is all basically ICP registrations. It's a work developed by Jens Belay, who uses surface or surface elements to match against the current point cloud, and uses a projection technique to project the world into a, like say, a local view, a range image of the scanner, and then does the alignment using the range scanner. And now you can see the robot re-enters a known part of the terrain, and then you will see the SLAM system kicking in and doing some corrections. So you saw the map shaking a little bit, and this was an optimization due to the post graph, something we will look into later in that course. But most of the registration you can actually see here was done using the ICP algorithm. So you can build consistent maps over extended periods of time using this technique, and it's a key ingredient for a lot of those SLAM systems which are actually out there. So this brings me to the end of the lecture today. So alignment of 2D and 3D data, point cloud data, data about our world, the geometry of the world, is an important task in perception, and aligning them is needed if you have multiple scans or observations taken from different views about the same environment, from different locations at different point in time, and you want to register those observations. This allows you to build first a consistent point cloud of the scene, but also allows you to estimate where the camera, where the sensor has been when taking this, when taking the observations. And the ICP algorithm is kind of the gold standard approach today for doing those computations, for calculating the transformation between 2 scans in terms of translation and rotation. Again, we have been looking here into data typically coming from a LIDAR or from a depth camera. So we ignored the scale information, which can play an important role if you look into cameras where scale information may be missing, but that's something we have not considered here. So what the basic approach assumes that we have an idea about the data association, so it requires an initial guess of the data association. And given the data association, this SVD-based approach is a very effective direct solution for actually computing the transformation. So for computing the rotation matrix and the translation vector that will align those 2 point clouds, assuming the correct data association. And this is, again, the major problem that we face today with the ICP algorithm, that this data association is not given. We don't know the correct data association. We need to guess it. We typically guess it based on the initial pose information that we have, for example, from odometry or from a GPS sensor or some other information. And if we don't have any idea about where we are, we basically have to make a brute force search, which is computationally very expensive and has also the risk of making wrong alignments, especially if you have perceptual aliasing. That means scenes which look very similar. So what the ICP approach does, it basically employs an iterative approach by computing a data association with one of the techniques I've described, given the first estimate of where the platform is, then performs an alignment, minimizing this error function, giving a new translation and rotation information. So I align those scans, and then I again check, okay, given this improved information, what does the data association look like? And I'm basically iterating forth and back. Data association, optimization. Data association, optimization. And do this in iterative steps until I basically don't do any update to my rotation and translation parameters anymore. And then I'm assumed to be converged. Several variants of the ICP exist, like point-to-point, point-to-plane, projection-based techniques, different outlier rejection techniques, all the things that we have discussed. And there's a full zoo of different approaches and also a few good overview papers which tell you in which situations you may use what, or what has been in all of practical examples shown to actually work quite well. In practice, we have to say ICP does not always converge to the correct solution. That's the main problem. But the main reason for this is mistakes in the data association, or the scene has changed, or different things, which all can be subsumized or described by the mistake in data association. So if we have the right data association, everything is good. If we don't have the right data association, there's no guarantees that we actually do a good job. In most situations, ICP works surprisingly well, but if you have to align hundreds or thousands of scans, there will be situations in which you make errors, and you need to take those errors into account in your SLAM system, for example, that you have ways for dealing with those outliers. There are different techniques that we will investigate in the remainder of the course, how we can deal with outliers. Again, one idea is RANSAC, a sampling-based approach, or optimizing not for squared errors, but using some robust minimizations or robust kernels in order to perform better here. But we are done for today, and you should have an idea on how to align 2D or 3D data taken from the real world from at different locations, but the same scene, and how we can align them. That means generating one consistent point cloud at the same point in time, get an idea about the relative transformation of the scanner locations when taking this observation. And this information is also something that we sometimes call virtual observation in the context of postgraph SLAM, and which will be exploited in the next lectures. With this, thank you very much for watching this video.